In this video, we're going to go over some practice problems on the content covered this week, and we're going to start with section 6.3 here. Now in this section, we learn how to simplify complex fractions, and we learn how to do so through two different methods. So please make sure you go through the lecture slides and the book to look at these two different methods. For the first two examples, we're going to use method 1. To use method 1, the first thing that we're going to do is simplify the numerator and denominator of our complex fraction separately, and then we'll multiply this fraction here by the reciprocal of this fraction, which is what we do when we're normally dividing fractions. Now for this specific example here, the numerator and denominator are already fully simplified, so there's nothing we need to do there. We can jump to the next step where we're going to multiply by the reciprocal. So we have k plus 1 over 2k is the fraction in our numerator, and we're going to multiply by the reciprocal of the fraction in our denominator, which is this here. So from here we can easily simplify. We have a 4k here and a 2k here. These guys will cancel, and we're left with just 2 here. So we're going to end up with k plus 1 over 1 times 2 over 3k minus 1. So just simplifying the 4k over 2k here. So from here we can multiply straight across. We're going to have 2 times k plus 1 over 3k minus 1. Now from here we can't simplify this any further, so this would be our final answer here. For this next example, we're again going to use method 1. So we're first going to just try to see if we can simplify the numerator and denominator of this complex fraction and then multiply by the reciprocal. So notice in our numerator here we have this fraction minus 1. So we can simplify this by getting a common denominator. So rewriting this with a common denominator, we'll have 2 over k minus k over k. So that'll be in our numerator. Now doing the same thing in our denominator here, we're just going to rewrite this with a common denominator. So we have 2 over k plus k over k. So we can simplify this further. Now that we have a common denominator in our numerator here, this just becomes 2 minus k over k. And similarly, in our denominator of this complex fraction, we're going to get 2 plus k over k. Now, our numerator and denominator of this complex fraction is fully simplified. We can't simplify this any further. So now we can multiply this guy by the reciprocal of the fraction in our denominator. So that would be k over 2 plus k. So doing so, these k's here will cancel, and we're left with 2 minus k over 2 plus k. And so this would be our final answer here. In the next several examples, we're going to simplify the complex fractions by using method 2. Now method 2 involves multiplying the numerator and the denominator of this complex fraction by the least common denominator of the fractions in our numerator and denominator. So every single fraction that we see here, we want them to have a common denominator. So for this one, it's fairly simple. The least common denominator, or the LCD in this case, would be x times y. If we want all of these guys to have a common denominator, we would have to multiply the top and bottom of this fraction by y, top and bottom of this one by x, and similarly for the fractions in our numerator here. So to use this method, like I said, we're going to multiply this complex fraction by our least common denominator. And whatever we do to the top, we have to do to the bottom here. Just like when we're trying to get a common denominator for a fraction, we have to multiply the top and bottom by the LCD. Same here for a complex fraction, we're going to have to multiply the top and bottom of our complex fraction by the LCD. Now this xy here is multiplying both fractions here and both fractions in our denominator. So we're going to end up with 3 times xy over x plus 3 times xy over y in our numerator, and then in our denominator, 3 times xy over x minus 3 times xy over y. So the whole reason why we're multiplying by the LCD is because it'll allow us to cancel some things, and then this complex fraction is going to end up being a little less complicated. So notice in our numerator here, these x's cancel and these y's cancel. So our numerator is just going to become 3 times y plus 3 times x. Now in our denominator, something similar happens. These x's and these y's cancel. So we're left with 3 times y minus 3 times x. Now notice that both terms in our numerator here share a common factor of 3, and so do both terms in our denominator. So we can pull out a 3 from our numerator. We're left with y plus x, and then a 3 in our denominator, and we're left with y minus x. Doing so, these 3's will cancel, and then our final simplified version of this complex fraction is going to be y plus x over y minus x. For this next example, we're again going to use method 2 to simplify this complex fraction, so we need to figure out what the least common denominator is going to be. So for this one, it's a little bit trickier. It's not obvious right away what the least common denominator could be. And notice here we have the difference of squares. So this tells me that we could factor this guy. In doing so, it might become a little clearer what our LCD is. So let's rewrite this complex fraction, and we're going to factor the denominator. So here we have y squared minus 16. Like I said, this is a difference of squares, so we know this is going to be y plus 4 times y minus 4. Now, it's pretty clear what our least common denominator is. It's going to be the denominator of this fraction, right? If we wanted to get the fraction in our numerator to have the same denominator as our fraction in our denominator here, we would multiply this guy by y plus 4. Doing that, we would see that our fractions in our numerator and denominator have the same denominator. So this tells us this factored version here is going to be our least common denominator. So the next step would be to multiply this guy by our least common denominator. So y plus 4 times y minus 4. And whatever we do to the numerator of our fraction, we have to do to the denominator as well. So we're also going to multiply the denominator of this fraction by the LCD. Now notice if we do this y minus 4 and this y minus 4 is going to cancel, and then everything in this denominator here is going to cancel with that. So we're going to end up with 6 times y plus 4 in the numerator, right? We're just left with this guy times this here. Then in our denominator, our LCD in the bottom of this guy canceled with this, so we're just left with 12 in our denominator. From there, the 6 and this 12 is going to cancel. We're going to be left with 2 on the bottom, and then our final answer is just going to be y plus 4 over 2. Alright, so for this last example here, we want to simplify this expression using only positive exponents. So to do that, the first thing that we're going to do is we're going to write each term in our numerator and denominator with positive exponents, and we can do so using this rule here. So in the numerator, rewriting this with positive exponents, we're going to get 1 over k plus 1 over p squared. And we're going to do the same thing in our denominator. We're going to have 1 over k for our first term. And for our second term here, this 3 is actually going to stay in our numerator, and the p squared is going to go in our denominator. This is because this negative exponent is only being applied to this p here, not to this 3. So now the problem becomes simplifying this complex fraction, and we're going to do so with method 2. So we know we need to find a least common denominator. So looking at the fractions in our numerator here, we can see that the least common denominator will be p squared times k. And then looking at the fractions in our denominator, we see the same thing here. So the LCD is going to be p squared times k. So we're going to multiply the numerator and the denominator of this complex fraction by p squared k. Alright, so multiplying p squared to both of the fractions in our numerator, we're going to end up with p squared k over k plus p squared k over p squared. Doing the same thing, we're going to get p squared k over k minus 3 p squared k over p squared in our denominator here. Now notice a bunch of things are going to cancel. Our k's, our p squared, our k's again, and our p squareds again. We're going to end up with p squared plus k in our numerator, and then in our denominator, we're just going to have p squared minus 3k. And so there's nothing further that we can do to simplify this, so this is going to be our final answer. Alright, so this brings us to section 6.4, where we're going to be solving rational equations. But first, in questions 11 and 14 here, what we want to do is give the domain of the variable in each equation. Now notice in question 11 here, this is a rational equation, and we know that this guy is going to be undefined whenever we have a division by 0. So what we need to do is we need to figure out for which x values will make each of these rational expressions here a division by 0. So we'll do this by setting the denominators of each of these rational expressions to 0 and solving for the variable. So we're going to set 4x plus 7 equal to 0. Solving for x here, we're going to get x is equal to negative 7 over 4. For this next rational expression here, we have 3 divided by x. So clearly, if x is equal to 0 here, it'll make this equation undefined. Then we're going to do the same thing for our last rational expression here. We're going to set this guy equal to 0. And then solving for x, we're going to get 13 over 6. So we can conclude from this that the domain of this rational equation here is all real numbers except 0, negative 7 over 4, and 13 over 6. So we can write this in set builder notation here. We do so like this. We say x such that x is a real number and x is not equal to 0, negative 7 over 4, and 13 over 6. Now for this next example, we want to do something similar. We want to figure out when the denominators of each of these rational expressions are going to be equal to 0. Now clearly we can see that'll happen when x is equal to negative 5 here and x is equal to positive 5 here. But we have this rational expression here, and it's not very obvious maybe right off the bat what x value will make this equal to 0. So what we can do with this polynomial expression in this denominator here is factor it first. So notice this is going to be the difference of squares. We have x squared and we have minus 25, which is the same thing as 5 squared. So factoring this, we get x minus 5 times x plus 5. So this is our new denominator here, and we still want to figure out which x values will make this denominator equal to 0. Well, using our zero factor property, we know that x minus 5 is going to be equal to 0, or x plus 5 is going to be equal to 0. We'll make this whole thing equal to 0. Now notice, solving for x here, we're going to get x is equal to positive 5 or x is equal to negative 5. So clearly, if we have these x values here and we plug them into this expression, we're going to get 0. But notice, if we were to also plug in x is equal to 5 into this expression, or x is equal to negative 5 into this one, we would also get 0. So we can clearly see that the domain of this guy is going to be all real numbers except those where x is equal to 5 or negative 5. So writing this in set builder notation here, our domain is going to be all x values, and this brace here, all x values such that x is a real number that is not equal to plus or minus 5. And we write it this way just to indicate that we're talking about positive and negative 5. So for the rest of this section, we're moving on to solving these rational expressions. So whenever we're solving these guys, the first thing that we like to do is to identify the domain. So looking at this, we can clearly see that for this expression here, 5 over 2x, if x is equal to 0, then we're dividing by 0, which is going to make this guy undefined. And similarly for this one, if x is equal to 0, this guy will be undefined. So this means our domain in set builder notation here is x such that x is a real number not equal to 0. So we just want to put that there so that whenever we get the solution to this guy, we need to make sure that it is in fact in our domain and that it is in fact a solution. If it's not in our domain, then it won't be a solution. Now from here, we can start simplifying this guy to solve for x. Now at first, what you might want to do is combine these fractions here. We can do that by getting a common denominator, then subtracting them, and then slowly starting to solve for x. However, with these rational equations, the easiest thing to do to first simplify this is to get rid of these fractions. And the easiest way to do that would be to multiply both sides of our equation by the least common denominator. So we're going to do that for all of these examples here. Now, the least common denominator for this equation here is going to be 4x. So we're going to multiply 4x to both sides of our equation here. And again, we're doing this because it's going to be the simplest way to simplify these fractions. Notice, if I multiply 4x on the left-hand side here, these 4x's are going to cancel. So on the left-hand side of this equation, I'm just left with 3 by itself. So I got rid of the fraction on that side. Now on the right-hand side, it's going to be a little bit more complicated. What we're going to do is we're going to multiply this 4x to both of these fractions here. So we're going to end up with 4x times 5 over 2x minus 7 times 4x over 4. And then from here, we can see that this is going to get rid of our fractions. We have 4x divided by 2x here, so we're just going to be left with 2. And then here our 4's are going to cancel. So our equation is going to become, we still have this 3 on the left-hand side. Then we're going to have 2 times 5, which gives us 10 minus 7x. Now this becomes a lot easier to solve for x. We're going to subtract 10 on both sides here. We're going to get negative 7 is equal to negative 7x. And so lastly, to get x completely alone, we'll divide by negative 7 on both sides, and we'll get that x is equal to 1. So that would be the solution for this equation. And we know that x is equal to 1 is definitely a solution because it's in the domain of this rational equation here. If we got that x were equal to 0 here, then we would say that there is no solution for this equation here because the solution that we got is excluded from our domain. But in this case, x is equal to 1 is within our domain, so we're good to go. All right, so for this next example, we're going to do the same thing. First, we want to figure out what the domain for this rational equation is. So notice that for this expression here, if x is equal to 2, we'll get 0, and if x is equal to negative 2 here, we're also going to get 0. So clearly those numbers need to be excluded from our domain. But for this guy, what we're going to do is factor it. We have a difference of squares here. Now factoring this, we're going to get x minus 2, x plus 2. And then using our zero factor property, if we set this equal to 0 and then solve for our x's, we're also going to get positive 2 and negative 2 in this case. So that means our domain here is going to be all real numbers except positive and negative 2. So we're going to write that here, and I'm going to write this in shorthand. I'm just going to say x such that x is not equal to plus or minus 2 here. But for all of these, our variable x is going to be a real number. All right, so the next step here is to multiply both sides of our rational equation here by the least common denominator so that we can get rid of these fractions. Now notice this guy here is our LCD. So we're just going to multiply this to both sides of our equation here. So from here, this LCD is going to multiply both fractions inside of our parentheses here, and then our LCD on this side is going to multiply this guy. So I'm just going to write down every single step here because it might get a little complicated. So we just want to keep track of everything. So 3 is going to multiply our LCD, or I'm sorry, 3 over x minus 2 is going to multiply our LCD. So this is our first term. Sorry, let's clean this up a little bit. Okay, then our second term, we're multiplying 21 over x squared minus 4 times the LCD. And then what I'm going to do is I'm going to keep this denominator, the x squared minus 4, in its factored form. And you might be able to tell why we're doing this already. These guys are going to cancel each other out. And then on the right-hand side, we're going to have 14 times, or 14 over x plus 2 times our LCD. And so we end up with this here. So from here, we can see that a bunch of things are canceling. These guys will cancel, these guys, and these guys here. So we're going to end up with 3 times x plus 2 for our first term, plus 21 for our second, and this will just be equal to 14 times x minus 2. So now we can distribute combine like terms and solve for our variable x. So the video cut off a little bit, but what we're doing here is this 3 is being distributed to both terms in our parentheses, so we get this here, and then we're doing the same thing with this 14 here, so we end up with this on the right-hand side of our equation. Now from here, we can combine like terms and solve for our variable x. So in this next step, what we're going to do is we're going to combine 6 and 21, and in the same step, I'm going to subtract 3x on both sides so that our x's are on the same side of our equation. Doing this, we're going to get this here. Now from here, we can add 28 to both sides of our equation. We're going to end up with 55 is equal to 11x. So lastly, to get x completely alone, we'll divide by 11 on both sides, and we're going to get x is equal to 5. Now the last thing here, we just want to make sure that this solution is in our domain. Remember, our domain is going to include all real numbers except for plus or minus 2. That means 5 is in our domain, so this is going to be a solution to this equation here. Alright, so let's do the same thing for this question here. First, we want to figure out what the domain of this rational equation is. So notice in this denominator here, we have 4x plus 7. So if we were to set this equal to 0 and solve for x, we would get that this will be equal to 0 when x is equal to negative 7 over 4. Now for this next fraction here, we don't have, our denominator will never be equal to 0, so we don't have to worry about this guy. Now for this one here, we want to do the same thing, but notice first, we could actually factor this guy. We can pull out the greatest common factor. Now in this case, the greatest common factor will be 3, so we're left with 4x plus 7 on the inside here. So if we were to set this equal to 0 and solve for x, we would find this will be equal to 0 when x is equal to negative 7 over 4, which is what we have for this rational expression here. So this means our domain is going to be, and again I'm going to write this in shorthand, so x such that x is a real number that is not equal to negative 7 over 4. Next, we want to multiply both sides of our equation by the least common denominator, and notice the LCD is going to be this guy here, 3 times 4x plus 7. So we're going to multiply both sides by that. So again, I'm going to write this in a fully expanded form so we can see what cancels, but we know that this guy is going to multiply both of these fractions here. So we're going to get 2 times this LCD, 3 times 4x plus 7, over 4x plus 7, plus x times this LCD, so we end up with this here, over 3. And on the right-hand side, we're going to get 6 times this LCD, over our LCD. So clearly we see that some things are going to cancel. These guys will cancel, these 3's here, and then this entire LCD here. So we got rid of our fractions. What we're left with for our first term is just going to be 6. For our second term, we're going to have x times our 4x plus 7. And on the right-hand side, we're just going to be left with 6. So from here, we'll distribute this x to both terms in our parentheses. Let's move this over. We're going to get 6 plus 4x squared plus 7x is equal to 6. So what we're going to do in this case is see if we can move everything over to one side of our equation, and then see if we can factor this guy, because we have this polynomial expression. So let's subtract 6 from both sides of our equation here. Doing so, we're going to end up with 0 on the right-hand side, and then these guys are going to cancel. So from here, we're going to get 4x squared plus 7x is equal to 0. Now, before we solve, or in order to solve for our variable x, what we're going to do is factor this guy, and we can do so by pulling out the greatest common factor. So that would be x for both of these terms. So we're going to be left with 4x plus 7. Now from here we can use our zero factor property. For this whole thing to be equal to 0, then this guy must be equal to 0, or this guy will be equal to 0, or both of them. So we have x is equal to 0, or 4x plus 7 is equal to 0. Now for this one, solving for x, we're going to get x is equal to negative 4. Our two potential solutions are x is equal to 0 or x is equal to negative 7 over 4. But remember, in our domain, we said that our domain consists of all real numbers except for negative 7 over 4. So that means this guy is not a solution. And our only solution then is going to be x is equal to 0. Now for the last question in this section, we want to graph a rational function. So before we graph this guy, the first thing that we want to do is find the domain of this guy. So again, we know the domain is going to consist of all real numbers except those that will make this denominator equal to 0. So we'll set x plus 2 equal to 0 and solve for x. Doing so, we're going to get x is equal to negative 2. So this means the domain for this rational function here is going to be all real numbers except x is equal to -2. So again, I'm going to write this in shorthand, x such that x is not equal to -2. So this means our function is going to be undefined when x is equal to -2. So this tells us we're going to have a vertical asymptote at x is equal to -2. So what we're going to do is plot that vertical asymptote here. We're just going to use a dashed line to emphasize this, that the function is undefined at this line here. So that also means that when we graph this guy, our graph is not going to cross this line here. So from here, the best way to graph this guy is just going to be to plug in numbers and see what we get for our output. And it's always important to plug in some numbers near this vertical asymptote too, so we can see how the function behaves close to this vertical asymptote. So as you can see, we plugged in some numbers here, and these are our output values. So we're just going to plot them on our graph here. So if we have -8, we're going to get -0.17. So somewhere around there. We have -3 gives us a -1. -2.5 gives us a -2. -2.1 jumps to -10, so right around there. And then -2.01, if you notice, is -100, which is off this screen here. So if we went to -1.9, so on the other side of this asymptote, then we're all the way at +10 here. So as you can see, we're never going to actually cross this asymptote. What the graph is going to look like is it's going to look like this here, and it's going to get super, super close to -2, but not actually touch that value. Now, if we look at values on the other side of this vertical asymptote here, so looking at -1.9, our output value is going to be +10. So we're going to have a point roughly around here. Now, if we plugged in -1.5, we're going to get +2. Continuing this process, -1 is going to give us a +1. This should be +1 there. 0 is going to give us a 0.5 value, so right around there. 1 is going to give us 0.33, so maybe right around there. 2, we get 0.25. And then lastly, if we plug in 8, we're going to get 0.1. So the graph of this guy is going to be this curve that looks something like this here. Now, we talked about this vertical asymptote that we have at x is equal to -2, but we also have a horizontal asymptote, and that's going to occur at, so we'll abbreviate with HA, that's going to occur when y is equal to 0. Notice, as we increase our x values in the negative and positive directions, our outputs are going to get closer and closer to 0, but not actually hit 0 or pass that line y is equal to 0. For example, here, if we had -3, that'll give us -1, and if we jump to -8, we're only going to -0.17. And if we were to jump to -20, this number would just get closer and closer to 0, but not actually hit 0. Similarly, for 8, in the positive direction here, we jumped from 2 to 8, that's a pretty big jump here, but our output value only jumped from 0.25 to 0.1. So this guy is going to get closer and closer to 0 as we increase our x values in both directions, in the positive and negative direction, but our outputs are never actually going to touch 0, so they're never actually going to touch or cross this line, and this is what's called a horizontal asymptote. So this would be the graph for this rational function here with our vertical and horizontal asymptotes there. Alright, so this brings us to section 6.5, where we're going to solve equations for specified variables and use proportional reasoning in word problems. So for this first question here, we're given this formula. We want to find this variable L given C is equal to 80 and B is equal to 5. So there's two ways that we could solve this. What we could do is we could just isolate the variable L in this formula here, or we could plug in these values for C and B first and then solve for L. Either way, you're going to end up with the correct answer, but in this case, I think we'll use the second method. So we'll plug in these values for our variables first and then solve for L. So if C is equal to 80, we're going to have 80 is equal to 100 times B, where B is 5, and this is all over L. So we want to find L, so we're going to have to isolate it. So the first thing we're going to do is we're going to get it out of the denominator of this fraction, and we can do that by multiplying by L on both sides. Doing this, we're going to get 80 times L is equal to 100 times 5, so 500. Lastly, to get L completely alone, we'll just divide by 80 on both sides. We're going to end up with L is equal to 50 over 8, and in simplifying this fraction, we'll divide the numerator and denominator by 2, and so we'll end up with L is equal to 25 over 4. For this next question here, we have this formula, and we're not given any values for our other variables, but what we want to do is solve for b. So all we're going to do here is just isolate this variable b. So the first thing I'm going to do is I'll multiply both sides of this equation by 2 to get rid of this fraction here. So we're going to multiply both sides by 2 here. So doing that, we're going to get 2 times a is equal to h times b plus d. Now, this h is multiplying this whole thing, so what we could do is we could distribute this h to both terms here. But what I'm going to do instead is I'm actually just going to divide this h on both sides. Doing that kind of saves us a step here. So 2a over h is equal to b plus d. So by doing that, we kind of got our b plus d term outside of our parentheses here. So from here, we just want to get b completely alone, so we'll subtract d on both sides. Doing that, we're going to end up with b completely isolated, and it'll be 2a over h divided by d. Subtracted d here. Alright, so in this next example here, we're going to get into proportional reasoning. We're told that wet snow might have a snow-to-liquid ratio of 5 to 1. So with this ratio, we want to determine how many inches of fresh snow would produce 3.25 inches of liquid. So this ratio here is snow to liquid. So as a fraction, we'd have our inches of snow on the top and our inches of liquid on the bottom. So what we want to do is we want to figure out how many inches of fresh snow would produce this much liquid. So as a fraction, we could write it like this here. We're going to put x on the top because that's our unknown value, the amount of snow that we're looking for. And in the bottom here, we'll put the amount of liquid that we have in inches. So as we know, this snow to liquid ratio is 5 to 1. So this means that for every 5 inches of snow, we're going to have 1 inch of liquid. So for every fraction that we have of this form, where we have inches of snow compared to inches of liquid, this can always be reduced to this ratio, this 5 to 1 here. So what we're going to do is set this equal to our ratio here, and then what we can do is solve for x. Now, to solve for x, what we're going to do is cross multiply. So we're going to multiply these two guys, and we're going to multiply these two guys together. Doing so, we're going to have x times 1, that'll just give us x, and that'll be equal to the cross multiplication of these two guys, so 5 times 3.25. So multiplying these guys together, we're going to get x is equal to 16.25 inches of snow. So this means that 16.25 inches of snow would produce 3.25 inches of liquid. And then in the beginning, I said that this fraction can always be reduced to this ratio here. We can check to make sure that that is the case here. If we plug in 16.25 into our original proportion here, and then reduce this fraction on the left-hand side, we would get 5 to 1 here. Yep, so just as a side note there, this proportion here can always be reduced to this ratio. So for this next example here, we're going to use these two formulas, and this says that rate is equal to distance over time, and then time is equal to distance over our rate. So for this example, we're told that Kelly's boat travels 12 miles per hour. So as a rate here, this would be 12 miles per 1 hour, so distance over time. What we want to do is find the rate of the current of the river if she can travel 6 miles upstream in the same amount of time that she can go 10 miles downstream. So to start off, let's let R be equal to the current of our river. So that's our unknown value, that's what we're trying to find. Now, we're talking about going upstream and downstream. So what we need to take into account is the current of the river in that case. If we're moving upstream, this will actually slow the boat down. If the boat can move 12 miles per hour, but it's going upstream, what we're going to do is take into account the current of the river. So the boat would be moving 12 miles per hour minus this current R. So by the same logic, if we were to move downstream on this river here, the boat would be moving power plus the current of the river. The current would actually be helping the boat move. So going back to this formula here, we know that the time is going to be equal to the distance over our rate. So the time that we're going to move upstream, I'm going to say is going to be TU. That's going to be equal to the distance that we're going upstream. So going back to the problem, we're traveling upstream 6 miles. So the distance is going to be 6. And then the rate here when we're moving upstream, that's going to be this 12 minus R, because we're taking into account the current of the river. So 12 minus R. Similarly, the time that it's going to take to move downstream, I'm going to call TD, is going to be the distance that we're going downstream, so that'll be 10 miles from the original problem, over the rate that we're moving downstream. So that'll be 12 plus R in this case. All right, so we have the time it'll take to move upstream and the time that it'll take to move downstream. And if we go back to this question here, it says that we can travel 6 miles upstream in the same amount of time that we can go 10 miles downstream. That means this TU and this TD here are actually going to be equal to each other. So we can set this guy equal to this guy. So we'll have 6 over 12 minus R is going to be equal to 10 over 12 plus R. So from here, we can solve for our variable R by cross-multiplying like we saw in the last problem. What we're going to be left with is 6 times 12 plus R is equal to 10 times 12 minus R. So from here, we can distribute this 6 to both terms in our parentheses here. We're going to get 72 plus 6R on the left-hand side. And on the right-hand side, we're going to get 120 minus 10R. So in order to solve for our variable R, we want our R's to be all on one side and then our constants to be all on the other side. So in one step here, I'm going to move this 10R over to this side and combine like terms. And in that same step, I'm going to subtract 72 from both sides and combine like terms. Doing this, I'm going to get 6R plus 10R, which gives me 16R, and then 120 minus 72, which gives me 48. Now solving for R completely, we're going to divide by 16 on both sides. So this tells me R is going to be equal to 3 miles per hour. So the current of this river is going to be 3 miles per hour. All right, so for this next example here, we're told that a chef can finish a catering job in 6 hours, and his student can finish the same job in 12 hours. And what we want to do is figure out how long it'll take them to do the job if they work together. Now, in order to solve this problem, we're going to use this formula from our textbook, and it says that the rate of work is going to be 1 over T of the job per unit time. So what this means is if the chef can finish a catering job in 6 hours, then he can finish 1/6 of the job per hour. So let's write this down here. So chef finishes 1/6 of the job per hour. And then for the student, they're going to finish, well, the job per hour. Now, if we think about what's happening algebraically, what we're saying here is that if they finish 1/6 of the job per hour, then we can multiply 1/6 by, let's call this x, which will be the number of hours worked. So if we multiply 1/6 by the number of hours worked, this is going to be equal to, we'll say 1, where 1 is going to represent one whole job. Similarly, for the student here, if they finish 1/12 of the job per hour, we multiply 1/12 by the number of hours that they work, they will finish one whole job. So If we were to solve for these variables here, for this first one here, to solve for x, we can multiply by 6 on both sides. This gives us x is equal to 6 hours, and that's exactly what we're told in the problem here. So this is kind of just like justifying how we're using this formula here. So similarly, if we were to solve for x for our student here, this would give us 12 hours, and that's exactly what we're told in the problem. It would take them 12 hours to do this job. All right, so let's get on with solving this problem here. We want to figure out how long it'll take them to do the job if they work together. Now, in order to answer this, what we're going to do is set up an algebraic expression. So we're going to let our variable x be equal to the hours. So that's how long it'll take them to do the job if they work together, and that's the value that we're trying to find. So we know it's going to take the chef 6 hours to do the job. So that'll be 1/6 of the job times the amount of hours that he's working. And then we're going to add 12 hours for the student to do the job. So that'll be 1/12 of the job times the amount of hours that they're working. Now from here, we want to figure out how long it'll take their combined workload to do one job. And as we said, we're going to let one job be represented by 1 here. So this will be our algebraic expression. What we want to do then is solve for our variable x. So what we have here is 1/6x plus 1/12x. So in order to add these guys together, we're going to need to get a common denominator. So for this first expression here, this will turn into 2 over 12x. And then we have plus 1 over 12x. This will give us 3 over 12 times x is equal to 1. So to get x completely alone, what we'll do here is we'll multiply by the reciprocal of 3 over 12. So that'll be 12 over 3 here. Because doing this, we're going to cancel this whole fraction here. Our 12's cancel and our 3's cancel. Whatever you do to one side, we have to do to the other. So we're going to multiply the right-hand side by 12 over 3. So on the left-hand side here, we've got x completely isolated. And on the right-hand side, we're going to have 12 over 3, which is going to be the same thing as 4. So that means it's going to take 4 hours for the chef and the student to work together to finish one catering job. All right, so this brings us to section 6.6, where we're going to be working with variation problems. So the first type of variation that we'll see is direct variation. We say that y varies directly as x if there exists a real number k, such that y is equal to x times that real number k. Another way to say this is that y is going to be directly proportional to x. Now the next type of variation is inverse variation. We say that y varies inversely as x if there exists a real number k such that y is equal to k divided by x. And then lastly, when we're looking at joint variation, we now have 3 variables. Y is going to vary jointly as x and z if there exists a real number k such that y is equal to k times our other 2 variables x and z. So the whole idea in these problems is to find our constant of variation. So we're going to work on some examples here, and these are just screenshots from our textbook. So let's look at question 37 here. We're told that if a varies directly as the square of b, a is equal to 4 when b is equal to 3. We want to find a when b is now equal to 2. So the first thing we're going to do is set up our variation equation. If a varies directly, we know that we're dealing with direct variation. So we're going to have a is going to be equal to our constant k times our other variable. Now in this case, our other variable is the square of b. So we're going to multiply k by b squared. Now from here, we're going to plug in our relevant information. A is equal to 4 when b is equal to 3. So we're going to have 4 is equal to k times 3 squared. And what we want to do is find this constant of variation k. So we know we're going to have 4 is equal to k times 9. And then solving for k, we're going to just divide by 9 on both sides. This tells us that our constant of variation k is going to be equal to 4 over 9. Now that we have this constant of variation, we can answer this question. We want to find a when b is equal to 2. So we're going to plug in our information into our equation. We're going to have a is equal to k, so 4 over 9 times b squared, and in this case b is 2. Alright, so then multiplying these guys, we're going to get a is equal to 16 over 9. All right, so for question 40 here, we're told that t varies inversely as s. So in this case, we're dealing with inverse variation. So we're going to set up an equation to represent this. So we're going to have t is equal to our constant of variation over s. Now, we're told that t is equal to 3 when s is equal to 5. So we're going to plug in that information and then solve for our constant of variation. So we're going to have 3 is equal to k divided by 5. All right, so solving for k, we're going to multiply by 5 on both sides here. And we're going to end up with k is equal to 15. So now we can answer this question. We want to find s when t is equal to 5, so let's plug in that information. We have that t is equal to 5. We know k is equal to 15. And we have 15 divided by s on the right-hand side here. Now solving for s, first we're going to multiply by s on both sides of our equation here. We're going to end up with 5, let's make that more distinct, 5 times s is equal to 15. And then lastly, we can divide by 5 on both sides to solve for s. We're going to get that s is equal to 3. All right, so for this next problem here, we're dealing with joint variation. We're told that f varies jointly as h and the square of g. So first we'll set up that equation here. So if f varies jointly as h and the square of g, our equation is going to look like this here. So doing the same process that we've done in the last several examples, what we're going to do is plug in this known information here and solve for our constant of variation. So we have that f is equal to 50, h is 2, and g is equal to 4. So we're going to end up with 50 is equal to k times, we have 4 squared, which is 16 times 2, so that'll give us 32. And then to solve for k, we're going to divide by 32 on both sides. So this tells us k is going to be equal to 50 over 32, and then simplifying this will be 25 over 16. So this will be our k value here, and I'm actually not going to box this because that's not our final answer. So to answer this question, we want to find f when h is equal to 6 and g is equal to 3. So we're going to plug these values into our equation here. Doing so, we're going to get f is equal to 25 over 16 times 54. So 25 times 54 will give us 1350. So we'll have 1350 divided by 16. And so we can simplify that. We're going to get 675 over 8. So this will be our value for f. All right, so now we're going to apply what we know about these variation equations to a couple word problems here. So for this first one, we're told that the weight of an object on Earth is directly proportional to the weight of that same object on the moon. So we know that we're dealing with direct variation here. Then what we want to do is use this information here to figure out how much a 50-pound dog would weigh on the moon. So when we're dealing with these word problems, the first thing I would do is assign variables to these quantities here. So for example, let's let the weight of an object on Earth be equal to x. So I'm just going to call this Earth. And then the weight of the object on the moon, I'm going to call y. So, if the weight of an object on Earth is directly proportional to the weight of the object on the moon, our equation is going to look like this here. So x varies directly as y. So now let's plug in our known information and solve for this constant of variation here. So a 200-pound astronaut would weigh 32 pounds on the moon here. So what we'll have is 200 is going to be equal to our constant of variation times 32 here. Now solving for k, we're going to divide by 32 on both sides. We're going to end up with k is equal to 50 over 8. So let's use this k value here to answer this question. How much would a 50-pound dog weigh on the moon? So we're going to plug in this information here. You're going to be 50 pounds on Earth, and then our constant of variation is 50 over 8, and then we want to solve for the weight on the moon, so y here. So what we'll do in order to get y completely alone here is we're going to multiply both sides of our equation by the reciprocal of this fraction. So we're going to multiply it by 8 over 50 on both sides here. Now doing that, these guys cancel and so do these, And then notice on the left-hand side of our equation, these 50s cancel also. So we're actually just left with 8 is equal to y. So this means a 50-pound dog would weigh 8 pounds on the moon. All right, so for our last problem here, we're told that for a given interest rate, simple interest varies jointly as principal and time. So the first thing I'm going to do is assign variables to these guys. So let's call simple interest our S here. Our principal is going to be P, and then time is going to be given by T. So this means that for a given interest rate, S varies jointly as P and T. So let's set up an equation for that here. That means S is going to be equal to our constant of variation times our principal times our time. Now for the next part of the problem, we're told that if 2,000 left in an account for 4 years earned interest of 280, how much interest would be earned in 6 years? So if $200 is left in our account, that's going to be our principal. So let's write down this information here. Our principal is going to be the $2,000. Our time is going to be 4 years, and our simple interest is going to be 280. So we're going to plug this information into our equation and solve for our constant of variation. So we're going to have 280 is equal to k times 2,000 times 4. So we're going to have 280 is equal to 8,000 times k, and then dividing by 8,000 on both sides, we're going to get k. So k is going to be equal to 280 over 8,000 here, and then reducing that, we're going to see that k is going to be equal to 7 over 200. Now we want to figure out what s would be equal to if our t is equal to 6. So we're going to plug in this given information here. Our constant of variation is this here. And we're still starting with this principal amount of $2,000, but now we're dealing with 6 years. So we're going to end up with multiplying this out. We're going to get this guy here, and then reducing this, we're going to find that our simple interest is going to be $420. All right, so that'll be it for this video.